So, you all know who our speaker is for tonight, but he asked me to give a little introduction. Bill Dunn is the Engineering Marketing Manager at Melly Associates, LLC. He has worked in the HVAC industry for 38 years, the last 22 of which for manufacturers rep firms that specialize in air distribution products. Bill was president of the Connecticut chapter of ASHRAE in 2007. Thank you. He writes a weekly humor column in the Republican American newspaper in Waterbury. He has authored 5 books, and he records a weekly feature for WJMJ, the radio station of Catholic Archdiocese of Hartford. Bill is very fond of the Red Sox, the class of 1975 homecoming queen, and Jesus. Not necessarily in that order. He is, well, I'm not reading this last part. Unacceptable. Unacceptable. He is looking forward to retirement in the next year or two. We'll see. We'll see.
All right. Thank you, July. Thank you guys for coming out here for the beginning of my farewell tour. So tonight's topic is direct drive fans. They are awesome. They really are, except when they're not. Okay? I don't know if you know, but there has been a major revolution in our industry in the last 15 years, a direct drive revolution. And by the way, anybody recognize this new up-and-coming rock band? For us boomers, it's actually new and up-and-coming. Of course, that's Led Zeppelin. So anyway, let me ask, who was working in the HVAC industry 15 years ago? Okay, all the past presidents. Who's been involved more recently? Okay, all you youngsters. So, you guys don't realize that in the last 15 years, it's been a total revolution. 15 years ago, almost all of the commercial fans and blowers were belt drive. Even little dinky 75 or 100 CFM fans were belt drive. I've been on a lot of roofs over the years, and I've seen these little fans where it's so small, the motor compartment is so small that the 2 pulleys are practically touching each other. But that's just the way we did it. I mean, from the time that Willis Carrier invented air, way back in 1904. No, he invented air, not air conditioning. And it really helps people breathing. That was good. Ever since the start of our industry, up until about 15 years ago, we just used belt drive for everything. Now, it's completely changed that the vast majority of fans are direct drive, even up to 50 and 75 horsepower motors, direct drive. So, the question is, why the change? Why did this industry that was the same for decades and decades suddenly in the last 15 years have this major change? The reason is, as you know from the fan laws, airflow is directly related to the speed of the fan impeller. The RPM of the fan wheel determines how much air you get. So, back in the day, most of the motors were constant speed. And it was really difficult to balance a fan when it's only going to spin 1 speed. We did try a few things. Anybody remember the inlet vane damper over there on the right? Yeah. So every once in a while we had a fairly big direct drive fan and no speed control. You bring power to it and it just starts spinning. And it delivers whatever air it's going to deliver. So we would put a damper, that one on the right, inlet vane damper, right on the inlet of the fan and start adding static to the fan to slow it down. You know, say for example, you had a fan, you wanted 3,000 CFM out of it, but when you energized it, it started running, it was delivering 4,000 CFM. So what we would do is just start adding static pressure, right it up the curve, get it to the point where now the flow is down to where you want it. So doing that makes the fan have to work against a lot more pressure. And using volume dampers to balance a fan, it does 2 things. It uses more energy, because the motor has to work harder to overcome the extra pressure, and it generates more noise. Now, I don't know if you guys have noticed in our industry recently, like energy efficiency is kind of a thing now. I don't know if you noticed. And I don't know if you've had any clients that spend 50 or 80 or $100 million building a brand new building, and they actually want it comfortable, including, they don't want to hear HVAC noise all day long. So balancing your fan by using more electricity and by creating a whole bunch more noise is not a real good strategy. So what we did for years and years was belt drive. Belt drive was king. Why? Because you could adjust the fan speed even though the motor speed was constant. And how do we do that? By adjusting the diameter of the pulleys. Just think of 10-speed bikes. You know, if you have a bike where the chain is riding on the sprocket with the big diameter, and then in the back it's on a smaller diameter sprocket, for every full revolution you make with the pedals, that back wheel is going to go more than a revolution, right? Or if you put it on the small sprocket up front and a bigger one in back, for every revolution you make with the pedals, the back wheel goes less than a revolution, right? Same thing with fans. This blower on the left, the two pulleys are different diameters, right? So whatever speed the motor's going, the fan's going to be going at a different speed, correct? Is it going to go faster or slower than the motor?
That case slower, yeah, the diameter of the fan's bigger.
Yeah, slower, because for every revolution the motor makes, this one's only going to go partial, because it's got a bigger circumference. This one over here, I don't know if you can see it, but the pulley that's on the fan is a smaller diameter than the one on the motor. So there, it's going to go faster. For every revolution that the motor makes, the fan's going to go more than a revolution. And that's how we would dial in our speed of the fan, which is how we balance it, by changing and adjusting the diameter of those pulleys. So what caused revolution to happen very recently? Was it George Washington, the father of the revolution? No, not really. By the way, I don't know about you guys, but if I was in a real shallow rowboat and the water temperature was like 27 degrees, I'm pretty sure I wouldn't stand up. You know, George, he was showing off with the CNN cameras, I guess. What caused the revolution was two things. First, VFDs. Now they've been around for a while, but in the last 15 to 20 years, VFDs have become more affordable, they're less expensive, more reliable, and with a smaller footprint. So they just started being used a lot more frequently. Get it? And as we all know, what VFDs do is they vary the speed of the motor by varying the input frequency supplied to the motor. They convert AC input power to DC, then convert it back to AC using IGBT power transistors and pulse width modulation. Okay, you guys probably figured out by now that I copied and pasted that off of a VFD website. Because I've been doing mechanical stuff for a long time, and I can tell you what the VFD does to the motor. I have no idea how it does it. What goes on inside, that's talk to an expert, like Kevin Wixom. ABB. So really, just to be honest with you, when it comes to electricity, I understand it about as well as a chipmunk understands algebra. So just, if you really want to know what's going on inside, ask an expert. Oh, there I am. X equals Y. But is it Y or delta? I don't know. I don't get it. The second big thing that happened was the introduction of EC motors, electronically commutated motors. These things are really interesting. They use a permanent magnet rotor, which makes it more efficient. But the big thing is EC motors have a control module built right into the motor with electronics that can control the speed. On some of the smaller ones, there's a little potentiometer screw right on it. The balancer can just take a screwdriver and dial in whatever speed he needs to balance the fan. On some of the bigger ones, we have there's a terminal strip we can bring a control signal, and the control signal just ramp it up and down as needed. So, for the first time in 100 years, we now can control the speed of the motors. And we don't need pulleys and belts. We can just, either with a VFD or EC motor, control the speed of the motor and do it easily and economically and reliably. So that's been a really, really big thing. And direct drive fans have a lot of advantages, they really do. First, less maintenance. There's no belts and pulleys and bearings, which are the main things that have to be maintained, usually every 3 months on the fan. They're not there. The motor is directly coupled to the fan impeller, very little maintenance. Next, lower cost. I put a little asterisk there. They're coming out with bigger horsepower EC motors now that are kind of pricey. But if you compare just like a small roof exhauster or a square inline fan, quarter horse, half horse, the belt drive version has belts and pulleys and bearings, extra stuff that costs money, plus extra labor to assemble it. The EC version is just boom, boom, put it together, you're done. So it actually can be lower price. Direct drive fans are easy to balance. As I mentioned, screwdriver, you dial it in, or you press buttons on the screen on the VFD, you're done. You ever see a balancing contractor balancing a belt drive fan? He's up on the roof, he's got a big toolbox in one hand, he's got a satchel in the other hand filled with pulleys, all different diameters. He's got to take his air readings and then shut everything down, take it all apart, loosen up the set screw, take the pulley off, put a new pulley on there, put it all back together, tighten it up, take another reading, still a little off, come back up, do it all over again with a different pulley, and it can take a balancer all morning to balance one belt drive fan. Direct drive with the little screwdriver, you can do 6 or 7 in the same time period. So, way easier to balance. Direct drive fans are more efficient. There's no drive losses. Anybody ever hear the term drive losses? Yeah, drive losses is the energy that gets created at the pulleys and the belts, turned into heat that never makes it to the fan wheel. So for example, if a particular fan needed 1.6 brake horsepower of energy to keep the fan spinning and maintaining the flow, the motor might have to output 1.8 brake horsepower. And some of that gets lost in heat and friction of the belts and pulleys. So right off the bat, you take your motor, connect it directly to the impeller, you're saving energy. It's anywhere from 3 to 15%. So it's significant. So direct drive fans are really good. And as some of you consulting engineers know, for the last 10 years, I've been telling you, go direct drive. Definitely go direct drive whenever you can. Now, who loves direct drive fans more than anybody? Is it consulting engineers or manufacturers reps? Oh, we like them, they're good. But the guys who really love them, facilities maintenance guys. Because it's so much less work to maintain them. And balancing contractors. Because they can go up on the roof with a screwdriver instead of 90 pounds of equipment and a satchel full of pulleys. So those are the guys who really like those. Direct drive fans truly are awesome, except when they're not. So let's talk about when they might not be so awesome. There are some disadvantages. If it's an inline fan, replacing the motor is a real pain in the neck on a direct drive fan. I don't know if you can see it here, but in the green here, this is the motor inside this housing. And not only is it hard to get at the motor, if you have to swap out a motor, or if it burns out, you gotta replace it. The minute you disconnect the bolts that hold the motor shaft to the fan wheel drops. It just drops down, and now it's a pain in the neck to get it back up in place to put the new motor connected. My colleague, Mike Casey, this morning gave me a brief 45-minute discussion about one of his projects about 10 years ago, Jackson Labs, and he has a whole bunch of direct drive inline fans. They were below the roof, right? And there was a stack above. They had sound attenuators on the discharge and sound attenuators on the inlet, and one of the motors burned out. And in order to replace it, they had to take all the ductwork and the silencer apart, drop the fan down onto the what was it, a catwalk or a mezzanine? And it took 4 guys 2 full days. If it was a belt drive fan, it would have taken 2 guys 2 hours to replace the motor. Here's a direct drive lab fans on top of a plenum, and good luck changing the motor out there if you have to. You probably got to call in a Sikorsky sky crane to hover above the building to do that. Now with a similar belt drive lab fan, the motor is outside of the fan housing. You just take off the weather cover, loosen up some bolts, disconnect the power, swap out the motor, put the new one on, put the belt back on, and the whole time you're doing that, the fan impeller down here doesn't move. It's being held in place by the shaft. It's not connected to the motor, it doesn't move. You replace the motor, put the weather cover back on, you're good to go. Much quicker. So that's just one thing. We don't always expect or plan the motors to burn out, but it happens. And if it does, a certain type of fans are a real pain to swap out the motor. Next disadvantage, the motor on inline fans is in the airstream, and a lot of times your airstream isn't all that clean. Here's a fan we use a lot. It's a all aluminum, cast aluminum housing inline fan. We use it for dishwasher exhaust. Works great for that, because no matter how moist the air is, no matter how much soap is in the air, it doesn't corrode the fan at all, like a steel fan would. But if you want it to be direct drive, the motor is right in the airstream. It's going to get soaked. It's not a real good for the lifespan of the motor. So with this particular one, if it is going to be dishwasher exhaust, we recommend put the motor someplace safe. Get it out of the airstream. Run it with a belt. We can put a belt tunnel on there to protect the belt so that doesn't get soaked. But it's going to be way better for the lifespan of the motor. And sometimes it's not just moist soapy water. It could be some kind of fumes or dirt, dust, chemicals. Just an inline fan, that motor is going to get just bathed in whatever's coming through the airstream. Here's another disadvantage. It's become a lot more tricky making selections. That's the official engineering term, right? Tricky. I remember the good old days. For the first 10 years I was working for Ken Hamilton at Air Equipment, I spent most of my time telling engineers that download the manufacturer software program. It's really easy. You make all your own selections. You can't go wrong. And on most of the selections, you plug in whatever type of fan you want. The CFM is static, and you get 4 selections. These are 4 sizes that land on a good spot on the fan curve. And we would always just automatically say, all right, the smallest one spinning real fast, throw that one out, too noisy. The biggest one spinning really slow, it's too big, too much metal, too costly. You pick any one of those 2 in the middle, you can't go wrong. It's real simple. Download the software, do it yourself. Well, now with direct drive, you get, on this same exact selection, 33 options. I couldn't show them all. This is just a screenshot. I had to scroll on my screen for a page and a half to show them all. There's so many more variables that play in now. And so for the last 10 years, I'm saying the exact different tune when I talk to engineers is, you know what, it's too tricky, it's too easy to make a really boneheaded mistake. Send me your blank schedule, I'll fill it out. I do this every day. I learned all the tough spots the hard way over the years. Just let me select it for you, really, because it's just, there's too many things that could go wrong. So it really is a pain in the neck now to do selections compared to the old belt drive days. Okay, another disadvantage. Let's talk about induction motors that run on VFDs. Okay, as you know, the speed of a motor is based on the frequency of the power and the number of poles that the motor is constructing. The two-pole motors spin the fastest, and in Europe they run on 50 hertz on their grid. Our electrical service here off the line, off the pole, is 60 hertz. Makes it go faster, but the number of poles determine how fast it spins. And as you know, the synchronous speed is actually the speed of the magnetic field inside the motor spinning, and the rotor's chasing that. It slips, it doesn't quite catch it, so if the magnetic field is spinning 3,600, the rotor is actually going 3,450. The most common fan we use is this one here, 4-pole, 1725 is the net speed. You know, again, what's going on inside the motor is a little vague in my head. I don't know if you know this, but when it comes to electricity, I kind of understand it about as well as a squirrel understands Shakespeare. You don't have another slide, Bill, do you? Seriously? Another one of your stupid slides? Oh, yes, I do. 2 amp or not 2 amp? That is the question. Okay, again, ask Kevin Wixom if you want to know what's going on inside the motor. All right, here's the thing. What'd you say? Okay. Direct drive fans are awesome, but what happens now, every once in a while, you have to run it above 60 hertz. Like this blower. For this particular airflow and pressure, here's the best selection. It lands on the best spot of the fan curve, best noise level, but it runs at 1845 RPM, which is common for a blower, especially if you're going against a lot of pressure. It might be 1900, 2100 RPM, that's common. But if your motor is 1725, back in the belt drive days, it wouldn't even be a discussion. You would just put on pulleys to make that 1725 motor deliver the 1845 on the wheel, no problem. But if you want to be direct drive, to get that RPM, you gotta run the motor faster than 60 hertz. You gotta run it at 64. Now, I found out over the last few years, there's a lot of very experienced people in our industry, by which I mean old guys like me, that have just got it in their head that you never run a drive over 60 hertz. And we ask why, I don't know, because that's what we always do. VFDs were, you wanted to slow the fan down, not speed it up. So 60 was always the upper limit. But the fact is, you could run a VFD above 60 hertz without any problem. Here's a summary of a table from NEMA, the allowable overspeed limits on running motors. And we'll look at our most common 4-pole motor. Up to 20 horsepower, you could run a thing up to 120 hertz without any problem on the motor. If your horsepower goes up to 150, you could run it up to 90 hertz. And then the last one, if your motor is a 300 horsepower motor, you know, like we use on bathroom fans all the time, you can run that thing up to 75 hertz without any impact on the motor. It's just that our mindset has always been 60 is the upper limit. It's really not. And sometimes we have to run it above 60 if we really want to use a direct drive fan. It's perfectly okay to run it above 60, as long as you don't exceed the nameplate amps. That's the key. You gotta make sure you have enough amps, enough brake horsepower there, don't exceed that, and you can run a thing at 64 hertz, 68 hertz. And I think we don't sell custom air handlers, but I've been hearing that a lot of the ones with the fan walls, with the fan arrays, those little plug things can run really fast. And they often just select it 72 hertz, 78 hertz. The fan does not matter, the motor doesn't care. So just, you have to kind of rethink the way we look at this stuff. That running above 60 hertz is fine, as long as you don't exceed the nameplate amps. All right, here's another issue. This is a little bit more serious. The fan manufacturers, if it's a direct drive fan, they have to provide, excuse me, they have to provide a motor that's large enough to handle the load if the VFD goes into bypass. That is, starts running at 60 hertz. Let me give you an example. Here's a selection, 3,000 CFM at 2 inches. So the best selection, the fan is 1351 RPM, 1.78 brake horsepower. So it needs to run at 47 hertz. Fine. If this was a belt drive fan, you would put a 2 horsepower motor on it and be done. But as you can see down here, if you can see it, we're not allowed to do it anything less than a 5 horsepower motor. And what they do at the factory, regardless of the manufacturer, they have to do it. They take your operating conditions, they plug it into a fan law calculator, here's our, 3,000 at 2, 1351, and 1.78 brake horsepower. And you say, all right, what's gonna happen if it goes into bypass? So, that would mean it's up to 1725 RPM, and you know how the fan laws are really fun when it comes to horsepower. As I mentioned before, the CFM varies directly with the RPM. You change the RPM, increase it 10%, you get 10% more air. But on the horsepower, whatever change you do, you have to cube it. So 10% more RPM means 33% more horsepower. 20% more RPM means 73% more horsepower. It's that cube effect, it really hurts. So what they do is they plug it in and they say, if it goes into bypass, this is our new operating point. We need a motor that can handle that, which would be a 5 horsepower. And this can be tricky, especially when the project gets bid and it's going through submittals, and it's very far along the step, and then the engineer says, hey, you submitted a 10 horsepower motor. You only need a 5. It's, oh no, you need a 10. Let me explain to you why. And then the engineer says, my electrical guys are gonna kill me. At this point in the project, if I say, oh, by the way, EF6 needs a 10 horsepower motor, redo your whole panel and all your the gauges for the wire that feeds power to it, they're gonna kill me. They'll throw me off the window. So we've had a couple of situations like that. They wanted to have a direct drive fan, but just because of where the operating point was at 47 hertz, needed a bigger motor. In case it went to 60 hertz, I had to say, well, I haven't said this in 10 years, but you should go with a belt drive fan. Because with a belt drive, the motor can spin 1725, the pulleys are different diameters, and it's not a problem. You go with that smaller size motor. So you see what I'm saying, how that works, how I can kind of box you into a little corner there?
Can you just choose to not put a bypass on?
Well, I've asked that question. What the factories have told me is that they have no control over what happens in the field, and they always have to assume the worst case. And even if someone said on the submittal, no bypass, it's just the VFD and that's it, they can't guarantee it won't be installed with a bypass, or that someone might not go over and start pressing the buttons and ramp it up. So, for one possibility that could go wrong, they have to use a blanket statement. You need a bigger motor.
If they ramp it up and it can't handle it, what's gonna happen? It's gonna shut down?
Yeah, the motor's gonna overheat, trip out. But they don't want that to happen. It's not that it hurts the motor, really, but they don't want that to happen.
But that
Yeah.
issue is with conventional motors, not ECM.
Correct, yeah, we're talking about induction motors, not ECM for you. Period.
Yeah, similarly, I just gotten some recent fan selections. It was 1.9 brake horsepower, and I was driving a 2 horsepower fan. I can't remember if it was on a VFD or not, but is that?
Okay, well, just in general, if your brake horsepower at your design conditions are 1.9, 3, go with 3. Because
Yeah.
you know how it happened once in your career where the duct you drew did not get installed the way you drew it?
Yeah.
That only happened once too, right?
Yeah.
They always do it exactly how you draw it. No, I mean, there's too many chances for, you drew a beautiful sweeping radius elbow, and they only have room to put in a mitered elbow, and then you forget to put the turning rings in, of course.
Yeah.
So you always want to give yourself some cushion there. If your brake horsepower is above 1.8, just go to 3. Don't even think about it, regardless of what kind of type of motor we're talking about.
Just in a pure motor, that one of my concerns or thoughts was, does the motor care, that close to it? Well, it doesn't sound like it.
No, the motor doesn't care. It's only if you need to speed the fan up to get the flow you want, and then it goes up into the service factor and beyond, then the motor cares, then it'll overheat and trip out.
Is it the service, you mentioned earlier about the amperage, well, I guess we're near the top end of the service factor anyway, so.
Yeah, I mean, the amperage and the brake horsepower right up very similar to each other.
So we're close, so yeah.
Yeah.
Thank you.
Okay. All right. Oh, there's a couple more disadvantages. You know how we said how the nominal speed of the motor at 60 hertz can be slower if there's more poles in the construction of the motor? Well, those extra poles take up space and are more weight, more metal that go into the construction of the motor. And so as you move up, same horsepower, it gets bigger and bigger and more expensive. So sometimes, if your design RPM is 800, oh, well, let's use a 960 motor, just slow it down a little bit on the VFD. The motor's so big, it might not fit if it's an inline fan. It's too big. Here, give you an example. These are all 5 horsepower motors. The one we use all the time, the 4-pole, 1725, it weighs 80 pounds. A 5 horsepower 860 motor weighs 180 pounds, more than twice the weight, and a much bigger frame size. And here's the real fun one, it's over 4 times more expensive. At the price of the motor is 4 times for the same horsepower. So even if it does fit, it might not be cost effective to go with the slower speed motor. So you can see how we were kind of like stuck between a rock and a hard place. Either go with a big expensive motor, keep the VFD from going way down, or have the VFD go way down and have a higher horsepower motor. It's like just really not a good solution sometimes. Except, yeah, just go with belt drive. Sometimes that's the answer. And here's another disadvantage, just hypothetically, just imagine that there was a worldwide pandemic. I know it's really silly to think, but just imagine that happening. And just imagine that there's a little shop in Illinois that's assembling EC motors, and they're waiting for one more microchip from Taiwan to finish the motor. And that microchip is sitting on a container ship anchored off of Long Beach Harbor, and all the longshoremen have walked off the job because they don't want to get COVID, and no one knows when that ship's going to get unloaded. And the fan that motor goes in, that used to have a 3-week lead time, now has a 20-week lead time. That might soon turn to 32-week lead time. We don't know. So about, when all this supply chain stuff happened 2.5 years ago, and it really started to hit, I made phone calls I never thought I'd make in a million years. I'd say, hey, you know what? That job you're working on has got to be done in 3 months. Well, funny thing, the fans you specified, they're going to ship in 6 months. And I haven't told you this in 10 years, but belt drive fans are really good. And the fan you need for this job, all the parts are on the shelf. They can assemble it tomorrow and ship it the next day, and it'll be on the job site on Tuesday. So, like I said, belt drives, they work fine. There's some disadvantages, more maintenance, but as opposed to holding up the entire construction schedule, maybe switching to belt drive is a good idea. Now, thankfully, in the last, say, 6 months or so, the lead times have gotten way better. I don't know what, I've heard that electrical stuff is still horrible, switchgear, still like 2-year lead time or something. But on the air moving devices, the ERVs and the fans, it's gotten way better. It's almost back to normal. But this issue with the supply chain and the microchips, it caused me to make some phone calls I never thought I was going to make. And it was really talking up belt drive fans after talking them down for 10 years. All right, let's talk about EC motors. They are amazing. That control module built into it is really cool. It just gives you so much flexibility. But EC motors have a tricky little thing. And when we first started using these 8 or 9 years ago, we didn't know about this at all, and we got burnt a few times. So you make a selection. I think this one, it was 900 CFM and 1/2 inch. So the software says you can do it with a 1.6 horsepower motor, and single phase 115, and the motor's doing 1725, and right down here, brake horsepower 0.156, and the fan RPM 1193. Okay, that looks good. Well, what we never noticed, and they didn't really go out of the way to tell us about it, there's a whole new concept called programmable max RPM. And what they do is, they take your initial conditions, your CFM and static and brake horsepower and RPM, and they plug it into that same fan law calculator, and they start going up slowly on the RPM and saying, at what point do we reach where we are maxed out at a 1.6 horsepower amp draw? In this particular case, that happens really soon. It's like 8 more RPM, and that's it. In the factory, they program the microchip to limit the maximum RPM of that motor. And we got a bunch of calls where the guy's like, the balancer's saying he's trying to speed this up. He needs a little bit more speed to get the flow he wants, It says 1725 on there, but he's around 1200, it won't go any faster. We pull out the paperwork and say, oh crap. The max RPM, that's right. It's been programmed in the factory. Now the same exact selection, if we had pulled down the menu at the top and made it a quarter horse, it would have jumped up and we got a whole lot more RPM to work with. But here's the weird thing about this. Go back to the 1.6. I don't know if you can see here, the list price for the motor is $852. That's list price. Contractors pay way less than that, but that's the list price. Now, if we change it to the quarter horse motor, list price is the same thing. You know why? It's the same motor. It's absolutely no different. Now, remember back in the olden days when a 1/2 horsepower motor was this big and a 3/4 was a little bigger? And as you got more horsepower, you got a bigger motor. It has more metal, more copper, more ability to draw current and generate mechanical work, right? With the EC motors, they often use the exact same motor, and it's not that it's a quarter horse motor, it's that it's rated as a quarter horse based on your initial operating conditions and where we limit the RPM to not exceed the amps for that particular rating. So the same motor, if we change this to a third, it would probably give us 1500 RPM. If we change it to a half, it'd be up to the full 1725. Same exact motor. They just use the microchip inside to control, limit the speed so it doesn't exceed the amp draw for whatever rating you're calling it. And the real fun thing about this is you can't change it in the field. You have to take the motor out, send it back, they reprogram it, and they ship it back to you. And contractors love that. And the reason, what I've been told, the reason that you can't reprogram it in the field is just like hypothetically, if you had 5 little 1/6 horsepower fans all tied into the same circuit in the panel, if they could in the field just go and reprogram to all be rated now for 1/2 horse, that would draw too many amps and it would in the panel it would be wrong. So they won't let you do it. We have to send the motor back or order a new motor and swap it out. It's a real pain in the neck. This is one of the main reasons why I've been telling engineers, you know what, just send me your schedule. And I'll select it, and that's the first thing I look at. Programmable max RPM, because that's what can really hurt you. And that's a thing that we never, ever had to think about before the EC motors, when everything was all belt drive. It just was so simple. It was, you know, the brake horsepower, if you're 1.8, bump up to 3. Couldn't go wrong. Now it's all these electronics building into it, all these limits on RPM. It's a real pain in the neck. It's real tricky. Does that make any sense? Is that, you know, and that's been a real, you know, we know a lot at our office. Most of it we learned the hard way. And I still can't get I've been begging the manufacturer to have it coded into their program. Hey, you know what? If these two numbers are within 10% of each other, don't let it be a selection. Force it to go higher. They're like, we're working on it. We're talking to our IT guys. So, I don't know. But it is very tricky. Yeah, and so here's a little snip from the middle of the page. It's the submittal sheet. And you know, you look at the motor information. 1.6, 1725, 115 single phase. And my question is, which one of those numbers jumps out at you? That one there that's inside the box? Or this one here that no one ever even thought to look at? Yeah, the box. And I don't know about you, but when I see asterisk and in fine print, later. It's in the box, I look at it. It's outside the box. So, you know, it's just one of those things.
And Bill, that's just because we need to tell the electrician something. We gotta say, size the wire for 1/6 horsepower, correct?
Right.
And that's,
Right, and that's why it gets to be a problem down the road if he's already laid that out and then, oh, by the way, we're gonna change the horsepower on all these fans. That's the bad time to tell him that. So, just to kind of wrap it up here, the main message is be aware that direct drive fans are great, but not always. not always. So really, with a direct drive fan, 60% of the time, it works every time. I don't know if you guys ever saw the movie Anchorman. It's so stupid, it's great. This is one of the funny scenes out of it. And just to kind of wrap it up, I don't know if you guys know this or not, but when it comes to electricity, I understand it about as well as a hamster understands the infield fly rule. I had to put something. I found this little video. I had to do it. That's right. That should be a ride at Disney World. Anyways, that's it. Any questions? Any comments, you guys? Yes, sir, Brian.
On that submittal slide you just had there, the RPMs that the state was selected for was, what, 1,200?
Yeah, the RPM that's selected was there.
Oh,
Yep.
okay, so then the rated RPMs was 1,700, then the reference where it says.
Yeah, what this is saying, although this is, it's not at all how we interpret this for the, the prior 100 years. That particular number is saying that this motor can go up to 1725 if it's programmed that way, if we increase the horsepower on this application, which that's never what that box meant before. And I discovered that the fan manufacturers, this EC technology came out, they were just kind of swimming against the tide, just trying to keep up with it. And they were buying the motors, putting in the fans, it was working great, but their software and understanding of it was still lagging, which meant our understanding was lagging. And we had a bunch of jobs 7, 8, 9 years ago that were really bad. Any other questions? Yeah, David.
Should we be scheduling that max programmable speed? Because that's really the motor's RPM once they ship it out. It's not going to hit.
That is the motor's RPM once it ships out. That's not a bad question. That might need to be another column on the schedule. It's nominal 725, but in this case, 1350 is the max.
But they're going to have to put in the big box with the schedule.
What's that?
They're going to have to put in the big box next to 1725
Oh,
for the schedule.
I think they should put this like about this big in here. 96 pitch right across the table. Anything else?
All right, thank you, Bill. That was great. I have a gift for you. Before I present your gift, I have great news for everyone. Anyone that wants PDH credit, Bill's presentation has been certified by the Practicing Institute.
Seriously?
There is. I had to pull a lot of strings for that one. But there's sign-in sheet right here. Come on up, get a sign the sign-in sheet, and I have a certificate for you. There you go.
Thank you, sir.
You're welcome.